right? So in all our previous discussion, we made use of a concept of a fluid element, right? So in all the cases, the fluid element moving through the flow field was the discussion. Now, what we will do now is we will move little closer to the fluid element, right? And we will watch more closely and pay attention to the orientation of the element and its change in shape. As it moves through the streamline, there is a possibility of change in shape, right? So we will look into that now, right? So I acknowledge John D. Anderson's fundamentals of aerodynamics, right? Now let us consider an infinite stimal fluid element moving in a flow field, right? So infinite stimal fluid element moving in a flow field. I want every one of you to have your notebook and follow what I am doing, right? Now the same fluid element, say this is a fluid element at a time t1 and this is the fluid element at a time t2. So as it translates along the streamline, the fluid element may rotate, right? So it rotates with a certain angle, whatever it is. And also there is a possibility that the shape may be distorted, right? It need not to be same like a cube, what we mentioned at time t1. It can change its shape also, right? So how to express that, right? So that is our discussion today. So let us consider this two-dimensional flow, right? For the simplicity, we consider the two-dimensional flow, right? And the two-dimensional flow in X and Y plane, right? X plane and Y plane. Here we consider the infinite stimal fluid element, but the two-dimensional element. So we can say that A, B, C, D, right, are the points, right? So here assume that the fluid element is moving upwards, right, and moving to the right. So at a time t plus del t, that is time t2, here the time is t, right? So as it moves from time t to t plus del t, there is a change in AB, and here if you see the AB, this is AB, right? Here this is AB, and here this is AB, and similarly AC. So we can say that there is a change in AB and AC. AB makes an angle, right? And similarly, AC makes an angle. So this is del theta 1. Okay, here it is del theta 1 and this is del theta 2. I consider the clockwise as negative and counterclockwise as positive, right? So please note this, then only we can do the derivation. So we have minus del theta 1, AB makes an angle minus del theta 1, and similarly AC makes an angle del theta 2. Right? So we have let us say the velocity. You have u, here it is u, and this distance is dy and this is dx, the elemental distance. And we can write if this is u, then this is u plus dou u by dou y into dy. Then similarly here v, we can write v is equal to dou v by dou x into dx, right? So now let us start. Now let us. So distance in y direction, please note the distance. Let us say the distance in y direction. Say that means that A moves during so we can write A moves during the time t plus del t, right? The distance. So we can write the distance as moving in y direction. If it is moving in y direction, then we consider v, and that we can write v into del t, right? V into del t. Now the c, we need to write the c, right? This is c. So if c moves, so let us write the distance in y direction. Distance in y direction, the c moves with the same time t plus del t, then we can write v plus dou v by dou x into dx into del t, right? So we can write that v plus dou v by dou x into dx into del t. Now we need to calculate the net displacement. Net displacement, right? Net displacement in y direction, same. So say in C to A, then we can write net displacement is V plus dou V by dou X into dx into del T minus V into del T. So we can finally arrive at dou V by dou X into dx into del T. That is what we have mentioned here. Dou V by dou X into dx into del T. So this is the net displacement in y direction of C, which is relative to A. Now, okay, now let us write the angle theta. We have theta. So let us write tan del theta 2. Tan del theta 2. This is theta 2, right? And you have the two components. So I want to calculate tan del theta 2, and you know this distance now, and you know this distance also. So we can write tan del theta 2 is equal to dou v by dou x into dx into delta t divided by dx. So that is equal to dou v by dou x into delta t. So when we consider del theta 2 is very small, then we can write tan del theta 2 be almost equal to del theta 2. So we can write del theta 2 is equal to dou v by dou x into del t, right? So similarly, you can consider the x component, right? The x component of velocity at point A at a time t, right? The x component of velocity at a time t, and then here similarly you can calculate the minus del theta 1, right? So I want you to calculate by yourself. Then I will write directly the say let us write tan minus del theta 1, right? So that can be dou u by dou y into del t. So we can write del theta 1 is equal to minus dou u by dou y into del t. That is already shown here. Dou u by dou y into dy is right. Similarly, okay. So now let us consider the angular velocity. What is angular velocity? This d theta 1 by dt and d theta 2 by dt is the angular velocity, right? So let us write the angular velocity. So we can write the angular velocity of A, B. This one we can write d theta 1 by dt and here d theta 2 by dt. Is the corresponding angular velocity. So let us write d theta 1 by dt, right? So that is equal to, we can say that the limit del t tends to 0, we can write del theta 1 by del t. What is del theta 1 by del t? Minus dou u by dou y. Similarly, d theta 2 by dt is equal to d theta 2 by dt is equal to dou v by dou x. Dou v by dou x, right? So by definition, the angular velocity of a fluid element as seen in the xy plane is the average of the angular velocities at line AB and AC, right? The angular velocity of this fluid element in this two-dimensional xy plane is the average of the angular velocities of line AB and line AC. So what is angular velocity? Say we can write the angular velocity as W Z. If this is the fluid element with the x and y, then with respect to z only you have the angular velocity. So let us write angular velocity Wz is equal to average of d theta 1 by dt plus d theta 2 by dt. So we can write it is of into dou v by dou x minus dou u by dou y. So this is the angular velocity in the z direction, right? About z direction. In the similar fashion, we can write the angular velocity in x, angular velocity in y. So if you want to represent the angular velocity for three-dimensional space, the angular velocity omega is equal to omega xi plus omega yj plus omega zk, right? So we can write finally omega is equal to half into omega x. So dou omega by, dou w by dou y minus dou v by dou z plus this is I plus 1 by 2 into dou u by dou z minus dou w by dou x plus here j, then 1 by 2 into dou v by dou x minus dou u by dou y into k. Right? So this is the equation for the angular velocity. So this equation expresses the angular velocity of the fluid element in terms of the velocity field, right? So this is the angular velocity in three-dimensional space. Right? So I recommend you to listen once again. Let us consider an infinitesimal fluid element moving in a flow field. This is a three-dimensional fluid element, and at a time t and at a time t2. So it means that the time t is t, t2 is t plus del t. Okay. As it translates in a streamline, there is a possibility that the fluid can rotate and also it can distort. Right? So let us consider a two-dimensional flow field in x and y plane, right? And this AC, here this is the AC, it is distorted, and similarly here this is AB, that is also distorted, and the omega Z is the component of angular velocity. So when you have a u component here and a v component here, u component at C is, the v component at C is v plus dou v by dou x into dx. Similarly, the u component at B is u plus dou v by dou y into dy. And we are looking into the change in the angle, that is del theta 1. Del theta 1 is the change in angle, but d theta 1 by dt is the change in angle with respect to time, and hence it is an angular velocity. So angular velocity, we first calculate this distance and this distance, and we have del theta 1, del theta 2, and hence we have calculated, right? This is del theta 2 and here theta 1, and angular velocity we know d theta 1 by dt. Then what we did is the angular velocity of the total fluid element is the average of the one in theta 1 and theta So we have taken off into d theta 1 by dt plus d theta 2 by dt. So that is equal to off into dou v by dou x minus dou u by dou y. Now for a angular velocity field, that is omega is equal to omega xi plus omega yj plus omega zk. So we have written the angular velocity in space. Now an important discussion, say I would like to show this angular velocity of the fluid element in the three-dimensional space, right? So if you see x, y, z, and you have omega, this omega can be expressed as omega xi plus omega y plus j and omega z k. This is what the angular velocity, right? Now, the angular velocity of a fluid element has an important role in theoretical aerodynamics, right? So, usually we express a component called 2 omega, right? So, the 2 omega, it is twice the times of the angular velocity, which is called as vorticity, right? Which is called as vorticity. So the vorticity is very famous in the theoretical aerodynamics. So let us consider vorticity is equal to 2 omega, right? And it is expressed by a simple zeta. So zeta, that is equal to 2 into omega. So what is 2 into omega then? Zeta is equal to, the half will go away. So dou W by dou Y minus dou V by dou Z I plus dou U by dou Z minus dou W by dou X. The same equation, but only thing is the half will go away. J plus dou U by dou X minus, sorry, dou V by dou X and dou U by dou Y into K. Actually, you can understand this from the notation, the dou W by not dou Z. In the other dimension, that is dou Y. Similarly, if you see all the component, see this is U, dou U by dou Z, not dou X. Because we already know that this is X and Y and Z. And this is U, this is V, and this is W. Dou U by dou Y, dou U by dou Z. That is the component involved in the vorticity, right? So, what is this? U, V, and W are the velocity component in the X, Y, and Z direction, right? So, what is this called? I mean, you have already seen this expression somewhere before. So, I can write this as beta is equal to, you have seen this before?
Del cross V.
Yeah, that's the point, right? So this is del cross B. So del cross V is vorticity. What is V? V is Ui plus Vj plus Wk. Now, in this velocity field, we can say that the curl of V is equal to vorticity. Right? Now, there is two important discussion. One is del cross V is not equal to 0, right? What is del cross V not equal to 0? This corresponds to, if del cross V is not equal to 0, say if this is not equal to 0, what it means? There is a change in W component with respect to Y, or any of this is existing. That means that the flow is rotational flow. Right? So it means that there is a significant angular velocity is existing. The second important condition, if del cross V is equal to 0, that means that it is a irrotational flow. Right? So that means that there is no angular velocity. No angular velocity. Right? So how can we say that, say for example, say the fluid element, let us draw a fluid element. Say this is a fluid element, and this fluid element moves through a streamline. Now, this is the streamline, right? As this fluid element passes through this streamline, it can have a change the fluid element have the rotation existing in this one. The fluid element is keep on rotating, right? Again, we can also draw in the other way. Say this is the fluid element, and the fluid element may change its shape. Right? As it moves through the. So this can be considered as rotational flow. Right? So what about irrotational flow? The fluid element, say if this is a fluid element, and this is the fluid element, and this is again the fluid element, and this is again the fluid element. There is no change. Right? Right? So we can say if the flow is irrotational, then the zeta is equal to 0. Right? Zeta is equal to 0. If zeta is equal to 0, then if you take in the dou v by dou x minus dou u by dou y, that is equal to 0. I mean, you can equate any one of these, right? So if dou u by dou x minus dou v by dou u by dou y is equal to 0, and this is a simple condition for the irrotationality in a two-dimensional flow. This is irrotational in 2D flow, right? Okay. So angular velocity and vorticity we have seen. Now we will go for another term called strain, right? Another term called strain. What is strain? Say we know already that this AB and AC, the AB and AC are distorted, right? So the AB and AC are distorted, and we can write at time t plus del t, there is a change in the AB and AC. So we can note that the strain is like, I represent this as del k, that is equal to minus del theta 2 minus del theta 1. So this is actually the here minus del theta 1, right? So we can define the strain in this way, right? So let us write the strain of a fluid element in xy plane is the change in k. If the change in k occurs, then there is a strain. So in general, the strain can be written as minus del k. So that is in turn equal to del theta 2 minus del theta 1. Right? So I recommend you to work out this strain. Strain, say, this is strain, then we should write something called time rate of strain. Time rate of strain. What is time rate of strain? Strain, this is time rate of strain. So we already know what is that, d theta 2 by dt minus d theta 1 by dt. What is d theta 2? Say I will write this time rate of strain in x and y, that is equal to dou v by dou x plus dou u by dou y. This is time rate of strain in xy plane. Similarly, yz plane, dou w by dou y plus dou v by dou z, zx dou u by dou z plus dou w by dou x. YZ plane and zx plane, right? So this is strain. This is vorticity, and we have a angular velocity. in 3D space, right? So I stop at this point for the today's discussion, right? Thank you.